some locomotives weren't just complicated. They were engineering fever dreams that made mechanics weep and accountants faint. Today we're counting down the 20 most stupidly complex locomotives ever made. The Southern Pacific AC-12 cab forward looked like someone built a locomotive backwards and forgot to mention it. In 1943, Southern Pacific took delivery of these 4882 monsters that ran with the cab at the front and smokestack at the rear. The reason was actually brilliant. Sierra Nevada tunnels and snow sheds trapped so much smoke that crews were literally suffocating. Moving the cab forward meant exhaust blew behind them. But this solution created new problems. The entire steam piping system had to be reversed. Oil fuel had to be piped over 80 feet from the tender to the firebox at the front. The throttle controls operated in reverse of every other locomotive on Earth. New engineers would instinctively push when they should pull, causing interesting moments. The mechanical stoker ran the entire boiler length. Water supply lines stretched impossibly far. Every maintenance procedure had to be reinvented from scratch. SP mechanics called them backwards engines and needed entirely new training. Southern Pacific built 256 cab forwards, the largest fleet anywhere. They operated until 1956, proving that sometimes the solution to one problem creates 20 new ones worth solving. The Pennsylvania Railroad T1 was what happened when Baldwin Locomotive Works convinced themselves they could reinvent the laws of physics. In 1942, the PRR introduced this 4444 duplex drive locomotive, featuring Raymond Loewy's shark-nose styling. The duplex design split driving wheels into two separate sets, each with its own pair of cylinders. This theoretically reduced hammer blow on the rails and allowed smaller, faster-moving parts. But here's where it gets complicated. The T1 used Franklin oscillating cam poppet valve gear instead of conventional valves. This system was designed for speeds up to 125 miles per hour, but proved nearly inaccessible for maintenance. Components were buried deep within the frame. When they failed, and they failed often, mechanics had to disassemble half the locomotive to reach them. The T1's real curse was violent wheel slip. The duplex arrangement meant each driver set had less weight for traction. At speed, one set would suddenly break loose, damaging the delicate poppet valves. Engineers called them slippery beasts. The PRR built 52 T1s, then scrapped them all within a decade. They proved that revolutionary and reliable are often mutually exclusive. The LNER A4 Hush Hush emerged from Darlington Works in 1929 looking like nothing British Railways had seen. Designer Nigel Gresley partnered with shipbuilders Yarrow to create a locomotive using water tube boiler technology from naval vessels. The theory was elegant. Water tube boilers operated at 450 pounds per square inch, nearly triple conventional pressure. Higher pressure meant more efficient steam and better fuel economy. The reality was a maintenance nightmare. The boiler contained a maze of narrow tubes that scaled and clogged constantly. Marine boilers worked because ships provided stable platforms. A locomotive frame shakes, rattles, and flexes with every rail joint. The constant movement caused tubes to work loose. Air leaked through breaches impossible to seal permanently. After a fortnight on the Flying Scotsman service, the W1 would spend weeks having components retightened. Crews nicknamed it the Galloping Sausage for its bulging profile. Out of 1,888 days since construction, the W1 spent 1,105 in workshops. That's 58% of its existence under repair. LNER rebuilt it with a conventional boiler in 1937. The water tube boiler survived until 1965, outliving the locomotive by 6 years. The Chesapeake and Ohio M1 steam turbine electric was the longest single-unit passenger locomotive ever built when it appeared in 1947. This 106-foot behemoth combined a coal-fired boiler, steam turbine, generators, and traction motors into one problematic package. The layout was bizarre. Up front sat a 29-ton coal bunker. Behind that came the crew cab, followed by a backwards-facing boiler, then the turbine and generators. Engineers had controls in front and boiler gauges behind, requiring constant head swiveling. Fine coal dust blew from the bunker, coating everything and shorting forward traction motors. The C&O ordered 3 at over $500,000 each to power their chassis streamliner. They claimed the M1 could make round trips between Washington and Cincinnati without servicing. In reality, they couldn't complete a single trip without mechanical troubles. Turbines designed for marine applications couldn't tolerate railroad jarring. Coal ash fouled everything. The locomotives were so long that turntables couldn't accommodate them. The chassis streamliner never entered service. All 3 M1s were scrapped by 1950, barely, 3 years after construction. Monuments to ambition exceeding wisdom. The Erie Railroad Triplex earned its nickname Matt H. Shea and its reputation as one of the most powerful yet impractical locomotives ever conceived. Baldwin built this 28882 monster in 1914 with 3 sets of 8 driving wheels, including 1 set mounted under the tender. The tractive effort was staggering. At 160,000 pounds of starting force, it could theoretically pull 650 cars, stretching nearly 5 miles. The problem was keeping it moving. The single boiler couldn't produce enough steam to feed 6 massive cylinders above walking speed. On the Erie, maximum velocity was 10 miles per hour. On the Virginian Triplex, it topped out at 5 miles per hour. The rear engine exhausted to atmosphere through a separate tender stack, reducing firebox draft. As crews used coal and water, the tender lightened, reducing rear unit adhesion. Baldwin built 4 triplexes, 3 for Erie and 1 for Virginian. None proved successful. They were relegated to pusher service on steep grades. Even there, they spent more time in shops than on rails. The couplers of that era couldn't handle the forces these locomotives generated. By 1930, all 4 were scrapped. The triplex proved raw power means nothing without systems to harness it. The Pennsylvania Railroad S2 steam turbine looked deceptively conventional when it emerged from Baldwin in 1944. Same basic shape as other locomotives, same driving wheels, same smokestack. But instead of pistons and rods, a 6,900 horsepower steam turbine spun inside that streamlined shell. The S2 used direct drive, meaning the turbine connected through massive gears to the center driving axles. Side rods carried power to outer wheels. It had 2 turbines, the main one for forward and a smaller one, 1,500 horsepower unit, for reverse. Above 40 miles per hour, the S2 was magnificent. British engineer E.S. Cox reported maintaining 100 miles per hour for 12 consecutive minutes. The smoothness was extraordinary. No hammer blow, no reciprocating parts slamming back and forth. But below 30 miles per hour, disaster struck. Turbines achieve efficiency at high speed. At slow speeds, the S2 devoured steam and fuel catastrophically. Boiler pressure could drop from 310 to 85 pounds per square inch during acceleration, causing thermal shock that cracked stay bolts. The S2 accumulated 103,000 miles before retirement in 1949. It proved turbines could work brilliantly at speed, but couldn't cope with the starting and stopping real operations demanded. The Bulleid Leader emerged from Brighton Works in 1949, looking more like a diesel than any steam locomotive in British history. Designer Oliver Bulleid created a fully enclosed, double-ended machine that could be driven from either cab without turning. It rode on 2 6-wheel power bogies, with all wheels driven through chain transmissions. Sleeve valves replaced conventional piston valves. The boiler sat offset to allow a corridor from each cab to the central fireman's compartment, and that compartment became legendary for the wrong reasons. The fireman worked in temperatures exceeding 140 degrees Fahrenheit, trapped between boiler and firebox with minimal ventilation. The original design anticipated oil firing, which never materialized. Coal dust and smoke filled the space. Crews worked shifts, measuring minutes, not hours. The sleeve valves failed repeatedly. Chains connecting driving wheels required constant attention. Firebox brickwork collapsed regularly. During trials, the Leader broke down so frequently it was towed back to workshops more often than it completed runs. British Railways cancelled the project in 1951. Only one of 5 ordered was completed. The Leader proved disguising a steam locomotive, as a diesel didn't make it operate like one. The Norfolk and Western Jawn, Henry stretched 161 feet from coupler to coupler when it appeared in 1954. This steam turbine electric was the N&W's desperate attempt to keep coal-powered locomotives competitive with diesels. Like the C&O's M1, it combined a coal-fired boiler with turbines driving generators powering traction motors. The name honored the legendary steel-driving man who raced against a machine. Ironically, this machine was destined to lose its own race against diesels. The John Henry generated steam at over 600 pounds per square inch, twice conventional pressure. Its tractive effort exceeded both the N&W's famous Class A and Class Y workhorses. On paper, it offered superior fuel savings to both steam and diesel alternatives. But paper doesn't account for coal dust infiltrating turbine blades and generator windings, or electrical components failing under railroad vibration. The controls resembled an airplane cockpit more than a locomotive cab. Even experienced crews struggled to master the systems. Each trip was essentially a test run. The John Henry spent more time in shops than on rails. The locomotive was retired in 1957, just 3 years after, for construction. It was the last steam locomotive designed for American mainline service. The Camelback locomotives forced engineers to ride perched atop the boiler, completely separated from their firemen. Built primarily between 1880 and 1927, these machines resulted from economics, not preference. Northeastern railroads had access to cheap anthracite culm, coal waste that burned poorly but cost almost nothing. Burning culm required massive Wootton fireboxes so wide they couldn't fit between wheels in the normal position. The solution was placing the firebox behind the drivers and mounting the engineer's cab astride the boiler, midway down the locomotive. This created a communication nightmare. The engineer sat inches above a roaring fire, surrounded by steel conducting heat and noise. His firemen stood on a tiny exposed platform at the rear, sometimes 40 feet away. They communicated through shouts, hand signals, or banging on the boiler with wrenches. In emergencies, this proved deadly. Injury records show Camelback crews suffered twice the accident rate of standard engines. A boiler explosion gave the engineer virtually no escape route. The Interstate Commerce Commission banned new Camelbacks in 1927. The survivors limped on until the 1950s. Reminders that cheap fuel isn't cheap when it costs lives. The LMS Garratt 260 plus 062 locomotives were the most numerous Garratt class in Britain, with 33 built starting in 1927. They were supposed to revolutionize heavy coal haulage between Towton and London. Instead, they became legendary headaches. The Garratt design placed the boiler and cab on a central frame, supported by 2 separate engine units carrying fuel and water. This spread weight across many axles and allowed a massive boiler freed from wheel constraints. For African and Australian railways, Garratts worked brilliantly. For the London, Midland and Scottish Railway, they became case studies in corporate interference with good design. The LMS Derby Design Office insisted on fitting their standard axle boxes to Bayer Peacock's proven design. These axle boxes were barely adequate for smaller locomotives. On the much larger Garratts, they overheated constantly. One passenger trial from Derby to St Pancras terminated at Leicester when an axle box failed. The Garratts were coal-hungry monsters requiring constant maintenance. wartime neglect made them worse. They lasted 25 years, averaging just 25,000 miles annually. The LMS Garratts proved that even excellent designs can be ruined by bureaucratic meddling. The Pennsylvania Railroad Q2 represented the most powerful non-articulated steam locomotive ever tested, yet became another victim of the PRR's duplex obsession. Built between 1944 and 1945, these 4464 freight haulers developed an astonishing 7,987 cylinder horsepower on the test plant. 26 were built featuring 4 cylinders, 2 driving wheel sets, and an automatic slip control mechanism supposed to prevent wheel slip. The controller used butterfly valves to cut steam when drivers spun more than half a revolution. Clever engineering that rarely worked as intended. Maintenance crews often skipped the complex system during overhauls because they couldn't keep it calibrated properly. The real problem was economics. At Columbus Shop, intermediate maintenance on a Q2 cost over $30,000 compared to less than $20,000 for the simpler J1 class 2-10-4. Performance between the two was nearly identical because the railroad's 50-mile-per-hour freight speed limit eliminated any horsepower advantage. When dieselization began, the Q2s became obvious targets. All were retired by 1951 and scrapped within a decade. The most powerful freight locomotives ever static tested proved too complex for real-world railroading. The Union Pacific Big Boy remains the most famous steam locomotive ever built, but few realize the maintenance complexity hidden beneath that enormous boiler. Also constructed 25 of these 4884 articulated giants between 1941 and 1944, specifically for the 1.14% grade over the Wasatch Range. They generated over 6,000 horsepower and could haul 4,000 tons unassisted where lesser locomotives required helpers. But the boiler tubes stretched over 22 feet long, approaching the maximum allowable length for any locomotive. These tubes were prone to bouncing and tearing, requiring replacement every 6 months to a year depending on water quality. Utah and Wyoming water was so hard that flue bundles clogged constantly. At full throttle, a big boy consumed 11 tons of coal and 12,000 gallons of water per hour. The articulated design required flexible steam joints connecting front and rear engine units. These joints demanded constant attention to prevent leaks. The firebox was so large that mechanical stokers were essential. Big boys operated for 20 years, but their maintenance demands helped justify dieselization. 8 survive, today in museums. 1 runs again, converted to oil. The New York Central Niagara class achieved something remarkable in 1945. Designer Paul Kiefer created a 484 locomotive that could average 26,000 miles monthly with near constant availability. Only 27 were built, yet they handled 12 trains daily between New York and Chicago, including the legendary 20th Century Limited. The Niagaras developed 6,000 cylinder horsepower, but this performance demanded maintenance procedures that bordered on theater. The 6-day-per-week operating schedule meant all weekly maintenance happened in 24 hours. Workers called hot men donned asbestos suits and entered fireboxes while locomotives were still in steam. The temperature inside exceeded 212 degrees Fahrenheit. Standing on still hot grate bars, they cleared tubes, repaired brick arches, and made repairs that normally took days. All references describe these workers as heroic. The 1946 steam versus diesel trials showed Niagaras performing closely with EMD diesels, but metallurgical failures in the expensive firebox wrapper doomed the class. None survived preservation. They were scrapped by 1956 for less than $15,000 each. Perhaps the finest 484s ever built lasted barely a decade. The SNCF 242A1 was André Chapelon's masterpiece, rebuilt between 1943 and 1946 from a catastrophically failed 1932 482 that barely ran at all. Chapelon transformed this lemon into perhaps the most efficient steam locomotive ever constructed. The 484 compound used one high-pressure cylinder, feeding two low-pressure cylinders, a triple Kilchap exhaust, and Nicholson thermic siphons. It produced 4,000 sustained horsepower, with peaks reaching 5,500, matching contemporary French electric locomotives. In 1952, the 242A1 ran between Paris and Le Mans, beating the best electric locomotive time by 16 minutes. From a standing start with a 600-ton train, it reached 60 miles per hour in 3 minutes. Efficiency was equally impressive. 20% less coal and 40% less water than British Coronation Scott locomotives of similar power. But here's the tragic irony. This brilliant machine was scrapped quietly in 1960 to avoid embarrassment. French railways had committed politically to electrification, and steam outperforming electric traction contradicted the narrative. The 242A1 proved steam could compete. Politics ensured it never got the chance. The South African Class 25, condensing 484 locomotives, solved a problem nobody else even attempted. The Karoo Desert offered hundreds of miles between reliable water sources, and conventional steam locomotives simply couldn't operate there economically. The solution was capturing exhaust steam, cooling it back into water, and reusing it. These locomotives hauled tenders larger than themselves, packed with radiator tubes and steam-driven cooling fans. Over 2 miles of radiator piping filled each tender. 6 massive fans drove air across the condensing system. On a good day, the system recovered up to 90% of exhaust water, stretching operating range to nearly 500 miles between water stops. The price was complexity that made mechanics weep. Radiator tubes clogged with scale from mineral-laden water. The fans demanded constant attention. The sheer weight of the condensing tender wore out rails and roadbed. Maintenance logs from the 1960s tell stories of crews spending more time cleaning fouled pipes than actually running trains. The condensers were brilliant solutions to impossible geography. They were also maintenance nightmares that consumed every advantage they provided. Steam in the desert, but only barely. The LNER A4 Pacifics hold the world speed record for steam at 126 miles per hour, set by Mallard in 1938. But that record came at a cost nobody mentions. Designer Nigel Gresley used conjugated valve gear that derived the inside cylinder's motion mechanically from the 2 outside cylinder valve gears. This eliminated one complete set of valve gear, simplifying construction and reducing weight. In theory, at least. In practice, the conjugated gear was exquisitely sensitive to wear. The mechanism connecting 3 cylinders through a series of levers and links required precise alignment. When bearings wore even slightly, the middle cylinder timing drifted, causing uneven power delivery and overloading. Mallard's record run damaged its middle big end bearing so severely that a stink bomb warning device fractured, filling the cab with sulfurous fumes. The locomotive limped into the next station and never attempted high speeds again. During World War II, roller bearings were replaced with plain bushes that wore faster. Middle cylinder problems became epidemic. Many A4s received reduced diameter pistons just to reduce overloading. The A4s remained fast and famous, but they required attention simpler designs avoided. The PRRS 16446 was the longest rigid-frame reciprocating steam locomotive ever built, stretching 140 feet from pilot to coupler. Baldwin constructed this single duplex prototype in 1939 with Raymond Loewy's stunning streamlined styling. The bed casting alone weighed over 97,000 pounds, the largest single-piece locomotive casting ever made. The S1 was designed to haul 1,200 tons at 100 miles per hour on level track. In December 1940 testing, it reportedly reached 101 miles per hour, pulling 1,350 tons. But the S1's size became its doom. It simply couldn't negotiate standard curves without overhanging into adjacent tracks. Turntables couldn't accommodate its length. The locomotive was restricted to the Chicago to Crest Line route, just 283 miles of the entire PRR system. The duplex arrangement concentrated only 46% of total weight on drivers, causing severe wheel slip, problems that plagued all subsequent PRR duplex designs. The S1 displayed magnificently at the 1939 World's Fair, where millions watched it run on rollers. Operating it proved another matter entirely. The PRR built no more S1 locomotives. The Bulleid-Garratt articulated locomotive represented engineering brilliance for impossible terrain. The design placed the boiler and cab on a central frame supported by two complete engine units, each carrying water or fuel. This spread weight across many axles, essential for lightweight colonial railways. The locomotives could bend around tight curves while hauling loads that conventional engines couldn't move at all. But Garratt complexity scaled with size. The largest examples featured boilers so massive they required water circulation pumps to prevent localized overheating. Steam passed through flexible joints between the boiler cradle and engine units, joints that leaked constantly under high pressure. The layout placed the cab between boiler and tender, exposing crews to heat from both directions. On the hottest examples, footplate temperatures reached levels that would be illegal today. Coal-fired Garratts demanded 2 firemen working shifts because fireboxes ate fuel faster than one person could shovel. Water tanks on engine units changed locomotive balance as they emptied. Garratts worked magnificently in intended environments. They also required specialized knowledge standard crews didn't possess. Training took months, maintenance forever. The Norfolk and Western Class A2664 locomotives represented the absolute peak of simple articulated steam development. Built between 1936 and 1950, these 53,000-pound tractive effort machines could haul coal trains that would have required 2 locomotives from any other railroad. The N&W designed and built them entirely in-house at their Roanoke shops, refusing to purchase from commercial builders. Every component was optimized for the railroad's specific operating conditions. The Class A burned coal from mines the N&W served, using massive fireboxes with mechanical stokers that could handle varying coal quality. But here's the unexpected complexity. The N&W maintained steam profitably into 1960, when most competitors had fully dieselized. This required developing maintenance techniques that approached artistry. Shop workers knew individual locomotives by their quirks. Articulation joints connecting front and rear engine units needed constant attention. Steam lines running between units leaked at joints stressed by curves. The N&W made it work through institutional knowledge accumulated over decades. When workers retired, that knowledge disappeared. The Class A represented steam perfection achieved through relentless human attention. The Pennsylvania Railroad's entire duplex program stands as American railroading's grandest engineering folly. Between 1939 and 1946, the PRR built 6 different duplex designs, totaling 55 locomotives, each attempting to solve problems the previous design created. The S1 was too long. The Q1's rear cylinders cooked next to the firebox. The T1 slipped violently. The Q2 cost too much to maintain. The concept seemed logical. Split driving wheels into 2 groups with separate cylinders to reduce hammer blow on rails and allow higher speeds. Each locomotive had 4 cylinders instead of 2, meaning twice as many pistons, valves, rods, and bearings to maintain. The division of weight between driver sets created traction problems that no amount of clever engineering could solve. Automatic slip controls added more components to fail. The duplexes performed magnificently on test plants where conditions were controlled. They struggled in the real world where weather varied, rails were slippery, and trains didn't cooperate with engineering assumptions. By 1952, every duplex was scrapped. The PRR's attempt to save steam from dieselization actually accelerated steam's demise by consuming resources. That could have improved proven conventional designs. And that's all, folks. These 20 locomotives proved that complexity doesn't guarantee capability, and sometimes simpler really is better. Don't forget to subscribe so you don't miss future explorations of engineering ambition. Here's another video I've specially selected for you. See you next time.